Hello everyone, I'm Joe Eappen and I'm a student of Purdue University. And today I'll talk about my work on distributing specifications in multi-agent systems done with my advisor, Professor Suresh Jagannathan. Consider a system where we have a specification that we need to satisfy, and say we want to use reinforcement learning for that. Now, reinforcement learning needs a reward signal to characterize the good behavior from the bad behavior. And so here we often use reward shaping to make this easier to show to the agent. And this design process is often done manually, but some people want to also do this automatically given a specification on the system. Now, from the specification, we could also feed uh, richer information to the agent about how to complete this specification. And there's been earlier work on this. One of them is spectral, where we where they use a temporal logic variant, and this is done on a single agent task, with the example being navigation in a 2D plane. And another work is reward machines, where this where they define a automata to capture the task at hand, and this is used to create the reward signal for the agents. We choose spectral as the basis for our work. So first I'll give a small introduction here. Now, spectral uses predicate functions, which are Boolean functions that have the input being the state S of the system. And the output here is a Boolean output, which is true if the predicate is satisfied. And each predicate also has quantitative semantics, where here it's a function giving a value which is real. And this is used to quantify the degree of this satisfaction of this predicate. Now, the relation between this and the Boolean output is that this value is always greater than 0 if and only if the predicate is satisfied at S. And as an example here, we see a reach predicate, which is defined for a goal P and a state S, where the quantitative semantics is 1 minus the norm between the state and the goal. So this predicate would be greater than 0 when the specification is satisfied. Now, to make these predicates into more complicated specifications, we have these functions such as uh, achieve and ensuring and semicolon being sequential, as well as or being choosing between two specs. And here as an example, achieve B is true when B is satisfied for this current trajectory at least once. Phi1 semicolon phi2 is a sequential specification. This means phi1 is satisfied and then phi2 is satisfied for this trajectory. Using this specification is non-trivial. First, we create a task monitor. This is basically a finite state automaton, but this has memory, and this is also used to capture the extent of the task completed at any given point. And this is needed since the tasks can be sequential, and this means the reward is non-Markovian in the state, in the sense it needs to know the history and what tasks have been completed as well. Now, using this automaton, you can create an augmented Markov decision process, which gives additional information about the task and the specification. And so here they expand the state space to include the monitor state of the automaton, which state it is in, as well as the action space, because we have choices between different tasks and we need to choose which task we're going to next. Now, this is given to the agent policy to decide, and the reward is shaped in a way that it automatically incentivizes going deeper into this task monitor until a final state is reached, which means the specification is satisfied. Now coming to multi-agent tasks in general. So here we have a clear distinction between the types of goals. They can be local, which are individual to each agent, as well as global, which need coordination among all agents. And these new problems require additional compilation and execution strategies because we still have problems with all multi-agent systems like coordinating decentralized agents as well as finding out which agents contribute to the global objective as well as the exploding state and action space when the number of agents is increased. And let's look at spectral for instance. So here, spectral is expressive. We can consider many different problems for a single agent task, but we need to enhance this for multi-agent problems. Also, spectral would be centralized if we naively use this, and this would be hard to scale, which is as shown by history, and that distribution will often help with this. Now, as an example here in the multi-agent world, we can consider a specification achieve reach P and achieve reach Q, where we achieve reach P first and then achieve reach Q. Now, if each of the agents has a state space SA, then the whole system has a state space SA power n. Say reach was defined on the whole state space S. This implies a synchronization. So here, all agents would need to reach P at the same time, and then all agents would need to reach Q at the same time. But if reach was defined on SA, now the predicate is localized to the agent. It can ignore the other agents during evaluation. So it can reach P and reach Q without any sort of synchronization between agents. Say we use a centralized monitor for this localized case. Now, since each agent has the task states being task achieved and task not achieved, and we have n agents, that means we have 2 power n states. And if there are k local subtasks, that means we have k power n monitor states. And so a centralized version would be hard to scale in this sense. But when we distribute this, now we have n times k states, since they're distributed over all agents and not needed to be captured by one agent, one centralized unit. And so here we can now mix these types of specifications together. So here you can reach local P, then reach local Q, followed by synchronization at R, which is a reach global at R. And what we do here, the key idea behind this is creating a composite task monitor, which has 2 different portions, one for the local portion and one for the global portion. And as well as distributing this over all agents to solve this scalability problem. But distributing this causes additional issues to arise, like synchronizing subtasks between agents. And also, this needs some sort of consensus method between agents during deployment so that they're on the same page, basically. One more thing we can do with these specs is find certain specifications that are amenable to a type of scaling, which we call MA decomposable specification. And so here consider n agents where phi eta comma n means that phi is satisfied for these n agents on a trajectory eta. Now, if you have a k, if you find a k, which is a number less than n, that has the following property, where phi being satisfied for all n agents means that it's satisfied for all agents in a partition of n, where we see each group individually, and each partition group has at least k unique agents. So here, just look at reach global P with 4 agents. This is also satisfied for all groups of 2 agents, since 4 agents can be considered 2 groups of 2 agents. So they're reaching P globally. And now you can say, but this is not a general property. If you see a spec collect X fruits where the robots have only a capacity of X by N fruits. We need N agents to satisfy the specification, and no less than N can. And using this property, you can make a scaling procedure, which sort of makes training easier. And you can start with this minimum group size based on this K value and a factor, which we increase the group size by. And at each stage, we multiply this group size by this factor to slowly increase the difficulty of the problem from an easier problem where there's fewer agents to a harder problem. And we reused the policy parameters from the previous stage. And here the total number of stages is logarithmic in the size of n. And this figure shows an example where we have 10 agents with 2 agents as the starting group size with a factor of 2. And this means there are 3 stages here. So we carry out experiments on a 2D navigation task where state and action space is 2D. And here, as a baseline comparison, we create an algorithm where we don't give the policy access to the monitor state, so it doesn't know which task it is in. And this makes it hard to synchronize between agents. And another baseline is the centralized version of Spectral, which sees the whole state as input to the policy. And we show the results on 3 agents and show some clear shortcomings here. From the satisfaction percentages shown here, we can see that the baselines can work fairly well when the spec is entirely global and has not many stages. And so the centralized version works fairly well. But as soon as we introduce local specifications, the centralized version is slower to converge, and the no monitor case also doesn't work well as the number of stages increases. And here we start to see the shortcomings of our baseline. Now, as we increase the number of agents, that is n, we turn towards this MAD composable scaling to help us learn a suitable policy. Now here we pass the learning stage as an extra input to the policy and start with a group size of 2 with a factor of 2 as well. And so for 6 agents, we have 2 stages where we start with 3 groups and then move to 1 group of size 6. So considering the same specifications as before, which is 5.1 and 5.3, by just changing the number of agents to 10 and 6 respectively, we see that the MAD composable scaling is crucial to get a policy that satisfies the specification. And for 6 agents, when we introduce a local stage, even the centralized version as well as this spectral without scaling cannot find a policy that satisfies the spec. And so here we see that this scaling approach is useful in many cases. And to show that this framework is more general, we also consider a StarCraft environment where here we define a kiting specification. And now kiting is sort of like moving close to an enemy and shooting it and then moving away. And then repeatedly doing that. So here the specification phi-SC does it 3 times, where all agents, where 8 agents, move away from the enemy in a global fashion, in a synchronized way. And then they move towards the agent within shooting range to take a shot. But they don't need to do this in a synchronized way. So this is a local predicate. And with this, the distributed disk spectral is stronger than the centralized case because because the size of the number of agents and the mixing of these local and global predicates. And with that, conclude here is that we need distribution to handle these general specifications for larger number of agents. And while existing approaches can express a large number of tasks, we need to adapt these for multi-agent problems. And here we still have some open questions like a better specification language and guaranteeing behavior on these systems after deploying. With that, I'd like to conclude my talk. Thank you for listening.